Recording in progress.
All right. So if you go, try and share my screen with all of you. So hopefully if you go to our Canvas website, you'll see that I put a new file up that says practice t-tests and ANOVA. So we will be working with that in Minitab today. If you're familiar with how to get data into Minitab, you can go ahead and do that. If you're not familiar with it, or if you get some really weird pop-up screens, which happens from time to time, I'll show you how to do that in a moment. With ANOVA, just to go over it again, what are a bunch of the different assumptions that we have to have when we're dealing with all of this? One, the data comes from a normal distribution. Two, the samples represent the population. Three, the variances of all the different groups are the same. And I was playing around on Minitab a couple days ago, and I noticed that there's a new test that they put on there. So we will take a look at that. And with that test, you don't necessarily have to have the equal variances. So we'll see how well that actually works out for that. And we also have to make sure that the data are independent, so independently collected of each other. So if this idea for the normal distribution is violated, there is a non-parametric test we can use since it's in Minitab, and trying to use the formulas to do some of these non-parametric tests are difficult. We're just going to look at how you push the buttons on the Minitab to actually get answers and take a look at what those answers mean. If the samples don't represent the population, it's just trash. So again, if these variances aren't equal, there is a test for ANOVA in Minitab now that we can do with that. But a lot of times you end up doing the same non-parametric test as talking about up here. And if they're not independent, there's an alternative test, which we're not going to get into in here, but you actually do have the ability to analyze that data. And I wish that the projector would display this stuff a little bit clearer for everyone. And I know I keep going over this stuff. Part of the reason is, like I've been saying, there are a lot of people when you get out into the real world who don't follow these rules, who don't check these assumptions. They get results. The software does not care whether or not the assumptions are valid or not. It's going to do whatever you tell it to do. And so you're going to get results. How good are those results actually going to be? Something that happened in real life, talking about option number 2 here, when the sample does not represent the population. When I was a student at Lawrence Tech, the university decided they were going to put out a survey to see or how many students would actually come to the university, what pricing options for per credit hour and all that were actually good. And they sent out a survey and they got a lot of responses. And the end result was the survey clearly stated it does not matter how much they charge per credit hour, they're going to get the same number of students. I happened to be at the staff and faculty meeting where they started talking about that. And of course, I heard that and it was totally ridiculous, totally dumb, knew that only fools and morons would actually believe that, and said, well, if that's true, if we drop our price to the same as, say, Oakland Community College, and we don't get more students, what does that say about us as a university? What was the response from the administrators? Oh, he's not a team player, blah, blah, blah. Well, how many of you in here have taken an accounting course before? How many of you are accounting students? So at about the same time, Lawrence Tech had a brand new accounting system put in. I might have mentioned this before, but the people in the accounting department did not know how to use their new software. So let's say you're the head of a department. You've got a $20,000 budget. You spend $10,000. How much is left in your checking account? Should be easy enough, right? The checking account, you don't make any interest on there does not go back into that account. It goes to the university's account. So you have $20,000 to start. You spend 10,000, how much is left? No one's that far in accounting yet. You can't answer that simple question. So it should be $10,000, right? Well, what happened? Because they didn't know how to use the accounting software, they ended up saying like, it's an expense. The software says it's an expense and automatically deducts that. And then they put in negative $10,000 because that's what they used to do with their old software. So the software looks at it, says it's an expense and is going to subtract it. What happens if you subtract a negative number? It becomes positive. So your new balance is now, according to the accounting department, $30,000. You now spend $25,000. How much is left in your account? Because it keeps adding, $55,000. Don't you wish your checking account actually worked like that at the bank or credit union? Eventually, they found themselves in some of the checking accounts they had. The bank that they dealt with were several $1 million in the red, meaning they owed several $1 million because some of the departments figured out what was going on and exploited it. Meaning they were buying $250,000 worth of brand new computers for all their labs every other year, when other departments couldn't figure out how to spend $3,000 to get new computers for some of their labs. And two of the things that happened were that summer, and this was actually the summer when I left, they doubled tuition. They didn't bother to tell any of the students that they doubled tuition. So imagine you signed up for your fall classes like you did. Let's say you've signed up for those classes back in July or something like that, maybe even earlier. You had everything paid off, and all of a sudden you get a bill for the exact amount of money that you just paid in mid-August. What's your first thought going to be? Oh, this is stupid. The accounting department doesn't know what they're doing. Because you already paid your $10,000 tuition, and then you get another bill for $10,000. September rolls along, you get another bill for $10,000, and now you have a late fee attached to it because you didn't pay it. What do? You go in and you show them that, or the accounting department, that, yeah, you actually made that payment, at which point they tell you, no, we doubled tuition, so you still owe this extra $10,000. How many students dropped out of the university after finding that part out? For the students that had transferred in from elsewhere, do you think they're going to stick around and put up with that? Or do you think they went back to whatever college or university they were at before? For the students that just started there as, say, a freshman or sophomore or something like that, didn't have anywhere to go back to, do you think they stuck around through winter semester? The university, well, honestly almost went out of business and almost had to declare bankruptcy. But according to the survey, it doesn't matter how much they charge, they're going to get the same number of students. And me being cynical and sarcastic, I'm just not a team player. And when I heard that, I laughed hard. I think anyone else would too, right? So what happened there? Again, what was the sample that they were talking to? Essentially, the only people that replied to the survey were people that were alumni. Do alumni of a university represent the entire population of people that might be enrolling in a university or might want? Exactly. So even though the university spent all this money on a survey and they had very clear results, because they did not have a sample that represented the population, the data is trash. Uh, and I've actually been in a couple situations where I knew the data was trash. And when you all get into your working world, you're going to run into situations where you know the data that you're looking at is trash. Then the question is, what do you do about it? If you're working for a big company and say your boss tells you you need to analyze this data, you recognize that it's garbage, and if you understand that perhaps the result of your analysis is going to have some major impact on the company, what's your goal? What do you do? Do you analyze the data and then watch as your boss takes that data and ruins the company and it goes out of business and you lose your job? Or do you say, hey, boss, this data is trash. Here's why it's garbage. We'll get results. They're totally meaningless. Do not make any decisions based upon it. Or do you just refuse and say, my personal integrity is more important than making my boss ruin the entire company? What do you go with? Who goes with personal integrity? Well, if you're not making that much money, you don't have much to lose, right? Well, what if you're making, say 150, 200,000 a year, you got a family and two kids or something like that? Well, you could lose your job today or lose your job in 6 months. If you, and if you, and depending on how bad it is, you can actually, like start talking with the people in the government, be a whistleblower and be like, hey, this is what's going on here. And then there's a potential that any money that comes out of it, you can actually, for the federal government anyway, you could actually get a cut of that money. So, but when you've got, say, your family involved, and let's say you know that if you would do this, you're going to lose your job in 6 months, what does that give you time to do? Yeah, update your resume, find a new job. So, do you go with integrity? Or do you go with the, say, safety and security for your family in the short term, potentially long term? It's a decision that sometimes you'll have to make, sometimes not. I hope no one here has to make that decision. Uh, Last time it happened with me, I told the person I was working with, um, every bit of data we have here violates pretty much every single one of those assumptions, and you're telling me to do the wrong thing. You hired me to be the data analyst. I'm telling you your data is garbage. What did boss man want? Well, I don't care, just do it. It was a part-time job. You know what? Screw it. No. And the person that I was working with, he found someone else to analyze the data. They tried to publish the data a bunch of different places after it was analyzed, and everyone at all the journals realized, no, this data is trash, and refused to publish it. And of course, I went back to him and was like, told you, you want to try doing better this time? No. All right, there you go. So anyway, and again, angry examples, right? So when we're looking at all the possibilities, if we pull up Minitab just really quickly, I'm not going to put any data in here just yet. But one of the things you can do to help you decide what you should be using, if you go to Stat and you bring up a little display here, go down to where it says non-parametrics. We were talking about uh, one sample t-tests. If the data you have is not normally distributed, if the data, well, basically, if the data you have is not normally distributed, we have this one sample Wilcoxon test. You can kind of hover over it and it says, determine whether a median of a sample differs significantly from a specified value. Use when data are symmetric. That should actually say when data are not symmetric, whatever. So you have non-normal data. You can use this non-parametric here. It's just a matter of clicking buttons. This man Whitney determine whether the medians of two groups differ when the data of both groups have similarly shaped distributions. So again, if you get into engineering or if anyone gets into like product and operations management, and you start looking at, say, how long do certain products last, and you start testing them for that, there should have the same distribution. It's not going to be a normal distribution. So you can use the man Whitney on that. Kruskal-Wallis, it says determine whether the medians of two or more groups. So this is the non-parametric version of ANOVA. So if we have this issue where some of your data are normally distributed, some of your data are not normally distributed, as long as they're similar-ish to being normally distributed, uh, there's same distribution, Kruskal-Wallis will work really well for that. And then we've got a bunch of other stuff on here that we really don't need to worry about too much. For today, though, we're going to do, well, first we have to get the data. So if you've already downloaded the data off of Canvas, it's just the practice t-test in ANOVA. I was going to try to have all this stuff set up for you already. And then I was like, you know what? I'm going to hold off for a minute. So it says data has column names. You need to make sure that you click on that. And I'm just naming these things different medications. Is that where this data comes from? Absolutely not. From time to time, if you open an Excel sheet that has, or workbook that has multiple sheets in it, there'll probably be an option here to open, say, sheet 1, sheet 2, sheet 3. The options here, not much going on with this. So I can go ahead and click on OK. And you can see that the top row here is where all the names of everything came in. And then each one of these groups has, or each one of these quote unquote medications has 10 samples in it. Again, is this data real? No. But it's here. I'm going to go back to Stat, down to ANOVA, And because of the way I have this data set up, this is going to be a one-way ANOVA. And because other software have different ways of trying to use and utilize data, if someone you're working with is using a program called SPSS and they want to do ANOVA, they have to have one column designated for the group that stuff belongs to. They have to have another column with the data in it. Here, all of our data is in different columns. So we need to come back here and say data are in separate column for each factor level. The responses we're going to look at, eventually we're going to look at all of these. When we look at all of these, when you look at all the plots and the graphs and everything, it is a lot, okay? So for right now, just so we can get an idea of what the graphs are going to look like and how we can interpret the graphs, and hopefully the graphs will auto format, so we might all even have a chance of seeing what these things are doing. I'm going to look at medication A, medication D, and medication G, just to start off with. Under options, says assume equal variances, so we will keep that selected for the moment. Confidence intervals, two-sided, confidence level, 95%. Again, with the confidence level, if we have small sample sizes like we have here, we'd probably actually want to change that. For right now, I'm just going to leave it at default. Comparisons. This is where what I was talking about last time, where if you click on the Fisher comparisons, what ends up happening is uh, we compare every group to every other group using essentially a two-sample t-test, but we don't make any corrections for it. And again, the issue with that, if we have 9 groups, 10 groups, 15 groups, and we do that, what's the probability that we're going to have everything working the way we want, or everything we said is true? Vanishingly small. Tukey is the one where you look at all of these different comparisons, and the probability that everything you say is true, or the way that we can think about it for now is everything we say is true is going to be 95%. So now we have to change the confidence intervals when we make our comparisons. You can also see here that there is done it and Sue, and you can see kind of what it says on here. Done it allows us to pick a control group. So again, depending upon the type of data we're dealing with, there might actually be a control group that we want to compare against, in which case we can click on that. And there might also be or you can see here with the Sue's test, it's comparing everything against the best, whatever that means. So if you happen to be working in, say, HR, and you have a bunch of people taking these different types of training, you can compare all the different groups to whatever seems to have the best results type of thing, okay? So we're going to look at these 3. Everything's going to pop up here. It's going to be broken down into different groups. There's going to be a lot that pops up on here as well. So I can come over here and I can just click on OK. For graphs, individual plot, individual value plot, box plot. Box plots are generally good. For the most part, when we start looking at the different regression models, we've got these residual plots. We're just going to click on all 3 or all 4 just to make it easy, which means there's going to be a lot of things popping up here. It can get confusing, so we're going to walk through it fairly slowly, okay? For results, This is all the data that comes out of here. Just going to click on OK. Storage. We may, sometimes having this information is actually useful. Sometimes it's not. For what we're doing here, I don't need any of this information. For stuff we do the next couple weeks, we probably will want this information. So I'm just going to leave it unchecked for now. I'm going to go ahead and click on OK. And a thing happened. Let's see. So this is telling us what we actually tested. This is telling us up here what we're basically testing. All means are equal versus not all means are equal. Alpha 0.05, so this is the 95% confidence interval. Equal variances were assumed. Is that actually true? We will see in a moment. We can scroll down here. And again, we have all this data. So what factor are we looking at, or what medication? How many samples do we have? What is the mean for each one of these groups? What is the standard deviation for each of these groups? So 15.5 versus say 9.9. We can do a test on that to see, are those two variances different from each other? We've got our confidence interval here. But something that we're going to have to get used to looking at is this pooled standard deviation, which is right down here. For doing the Tukey comparison test, they try to make this as easy as possible to understand. But when we start looking at some of these, especially when we look at all the data, this can get to be really, really horrible. So if you look here, it's actually switched around the order of everything we're looking at. And what this is trying to say here is we can't tell the difference between medication A and medication D. It's also saying we can't tell the difference between medication A and medication G. But it's putting medications A and G in one group, medication D and medication A in the same group. So this is trying to tell us essentially, uh, if in this case, if we're trying to figure out, say, what is the best medication, and we're looking at, say, what is the largest value here? Well, you can see that the mean for group D and group A, 27.6, and then 26.88, so 26.9. Those are both in the same group. We can't tell them apart at this point. But we can say medication G just isn't cutting it. We can get rid of it. But at the same time, based upon the data, this is saying that we can't tell the difference between medication A and medication G. And what did I just say about medication G? It's not cutting it. And it's saying that medication A is in that same group of drugs that just aren't cutting it. But it also says that it's in the same group as the drug that is cutting it. So how do you handle that? Looking at what we have here, I would actually just go with and say medications A and D. They're similar enough. We can't tell the difference at this time. This is where the type of graph that gets really, really awkward really quickly. So I'm going to send this to Word. And if it'll let me send it to Word, all right. And no, I still haven't figured out how to make these things have any bigger. But basically what this is saying here is looking at medication D versus A. So this green dotted line here is telling us that there is no difference between these two groups. So this is saying medication D and medication A, we can't tell a difference between them. Looking at this, so medication G versus A, you can see that the difference between the two groups seems to be a negative value. But it does come up and just touch this dotted green line, which is where we get some of this ambiguity from. This last one we can see, again, that it's a negative value, but the bar out here does not touch the green. So that's telling us that there is a big difference between medication D and medication G. And looks like it's about what, maybe a 15.5 point difference, whereas this might be a 14.5 point difference type of thing. So when we're looking at these, this is telling us that D and G are definitely different. Going back to Minitab, this thing right here is telling us that medication D and medication G are definitely different. We look at the next group here. So done it multiple comparisons with a control, grouping information using the done it method and 95% confidence. So we called medication A the control. This is telling us that A and D are similar to each other, but medication G, again, just not cutting it. Because we're only doing 2 comparisons instead of 3, we can see that medication A and D, we can't tell a difference between them. Medication A and G, and you see right here that it's a G minus A, so small value minus a larger value. That's why we're getting this negative value here. We come up here, look at Sue's system, A and D, and then D and A. So it's comparing A versus D, then D versus A. Do we really need to make those 2 comparisons? If I say the left side of the class versus the right side of the class, and then want to do, okay, the right side of the class versus the left side of the class, does that make any sense at all? Does that make any difference? No. But software is just doing it automatically. And then it's already decided that I believe it's what medication D is the best because you can see up here, level mean, largest of other level that means for everything that we took. So that's telling us we're looking at the largest value and comparing it against that. And this is kind of telling us uh, D and G, they are maybe not, or they're a bit different. Interval plots. So again, you can see, does the variance for all 3 of these things look like they're fairly similar? How can we tell looking at the size of these error bars here? Do they look about the same? If they do, that's usually going to be good enough. Looking at the box plot of the data, this is telling us a little bit different story about the variability of, say, medication G versus medication A. But this is the kind of stuff here that we really need to be concerned about and need to get an idea about. So I will pull this up into Word. When you all took DS 301, did you guys get into QQ plots? Okay. So my personal opinion is this QQ plot thing here should probably go away. But it is a standard way of looking at data and trying to determine, do the data you're looking at say conform to the distribution you are assuming. So what do I mean by that? With this normal probability plot, we are assuming here that there is a normal distribution. As long as these dots tend to be close to the red line, that's a sign that they are normally distributed. Remember, one of the assumptions that we have for ANOVA is that the data is normally distributed. This, the way that it looks right here, is kind of saying, yeah, it looks normally distributed. Looking at the fitted values versus residuals, this is another way to tell, does there seem to be a large variation difference between the groups? Again, it's visual. Could you look at this and say, well, look at this value here versus this value, calculate the distance between them, calculate the distance between bottom and top here, calculate the distance, and then try to do a comparison? You could. But in statistics, a lot of stuff that we do is based on basically just looking at things. Why do a lot of statisticians tell you that you need to just look at things? Because that's how they did it in 1925. Creating a plot like this in 1925 by hand takes some effort, but you can do it. Creating a plot like this by hand in 1925 takes some effort, but you can do it. Some of the stuff that we can do with our software now, you literally 1925 would have been impossible, or would have been so complicated that no one would bother to do it. Okay. And the last thing here is we're looking at the residuals and plotting them on a histogram. Again, if these are normally distributed, and again, this is a visual thing, but you start low, does it go high in the middle and then come back down low again? Essentially, that's what it does. This plot or this bin right here is a bit off. Did I talk with all of you about bins and histograms? I, I've, I've only got 4 stats classes this term, so I don't remember who I said what to. So if I keep repeating myself, yes, I am going crazy. Thank you for noticing. But anyway, when you're making a histogram like this, I actually like the psychology departments and psychology stats version of a rule of thumb for these. How many data points do you have? Take the square root of that and then look. So we've actually got like 30 samples here. So 30 samples, you take the square root of that, you're going to get a number between 5 and 6. So how many bins should we really have here? 5 or 6. How many do we have here now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is major overkill. So if we wanted to try and redo this histogram, if you go into Minitab and into some of the sub menus, you can actually do that. Since we're using the residuals here to make the histogram, we can go into Minitab. We can actually manipulate it and get all those residuals by clicking on that one box for an option, and then make our own histogram. Based on what I see here, low on the outside, higher in the middle, because of the small sample size, it looks normalishly distributed to me, or at least close enough. Since this says it looks good, I'm not going to worry too much about what this says down here, okay? And how do you train your eye to see all these different things? Basically, you have to have a couple dozen different stat classes or start working with data and doing these types of analyses all the time, which is time consuming. And I know that when I was taking some of my first couple stats classes, I could look at some things and go, no, that's not right. And then what the professor say? Oh, you're just not experienced enough. If you're really good and if you've been doing this for a while, you'd realize that it is fine. All right, boss, whatever. So we've got that analysis here. We can go back to stat and back to ANOVA, back to one way. And this time I'm going to click off that assume equal variances thing. Click on OK. When I go to comparisons, I now only have one option. So that's the option I have to choose. Then click on OK. Graphs, all of that has already been selected by us. Results, all of that has already been selected by us. Storage, so if we wanted the residuals to create a histogram, let's say 5 or 6 bins, I could click on there. Again, I'm not going to worry about it with the data we have. Then I'm just going to click on OK. Now I'm going to click on OK one last time. So what happened? If we look at what happened, yeah. All right. Back to stat. Back to ANOVA. One-way ANOVA. Once we are here, we go to options. There's this one thing here where it says assume equal variances. Initially, that was clicked. At least on my side, that was clicked. I just clicked on there to make it go away. And then for comparisons, before we had Fisher, Tukey, Sue, and Dunnett. This time we only have one comparison. Okay. And I'm going to come down here and click on OK. Everything else is ready. I can just go ahead and click on OK. But if I did that, it'd give me everything that I've got on here before. So if we're looking at the data that's up here, the means are all the same. The standard deviations are all the same. The confidence intervals for those means are the same. But what is this telling us here? We had previously assumed that all the variances were equal. And we had DNA were in one group, and then G was significantly different from those two. What's happening this time? It's telling us that all three of these groups seem to be the same. We can't tell the difference between them. If you look up here, the p-value is really close to our point, or being below our 0.05. It's not there yet, but it is close. But this is actually telling us here, when we do this analysis, where we don't assume equal variances, there does not seem to be a statistically significant difference between these three medications. It's also suggesting that perhaps there is a statistically significant difference between the variances here, which when we assume it's equal variance, you get one set of results. When we don't make that assumption, it's given us almost completely different results. So this is a way of checking our data, checking what we're doing, and making sure that we're actually getting the correct information. And when we look at all the different information here, now these confidence intervals here are pretty much all the same. And they're all saying that it seems like it contains, or these confidence intervals contain 0. If a confidence interval contains 0, it's telling us that we can't say there's a difference between it. Even though here, going from 0 to this point, so 0 to 29 on one side, then 0 to what? 2 on the other side. Because we've got the 0 in there, we can't say that there's a significant difference going on here. Same individual box plot, or interval plot, same box plot, same everything we had before down here. So what's going on with all of this? When we assume equal variance, we found a significant difference. When we don't make that assumption, what do we find? There's no significant difference. Which one do we go with? Well, you go with, if we have a way of testing the variances of all of these, that tells you what the right thing is to do. Another thing that we can do is go down to that non-parametric. So stat non-parametric, and because we've got the three groups, Kruskal-Wallis, once we've got there, now, so this is going to require us to have everything in a column. Sorry about that. I didn't know that that was going to be a thing here. So I'll skip that for now. But one of the things that we can do, and one of the things that's going to be annoying for most of you, is from time to time you have to do something called data prep. So apparently to use the non-parametric method, we'll have to come out here, create like a new column, call it medication, and then don't do this right now. But just as an example of some of the fun things you get to do with data prep, I have to come out here. Okay, we're going to have all these A's. Now I take everything from medication A, copy cells, paste. Result. Now I come down here. We're looking at what? A, D, and G. So copy this, paste it over. Come over here to G, copy, paste, G, 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 G. That was almost fun and entertaining. But sometimes when you have data, you actually have to spend time trying to get it into a format that the software will understand. And looks like a couple of the data points didn't even make it over. Let's see. So copy those. Replace the active cell. No, that's not. So again, some of the fun of dealing with this software. Let's see if it happens if I say cut cells. Okay, that brought that up. If I say that's A, so that should be good enough there. Now let's see if this actually makes it work. Depending on the software you use, you can have all these different factors come up. So response is result, factor, med, okay. All right, so a thing did just happen there. So this is telling us the medians for all of our data, the different rankings, blah, blah, blah. But so this is looking at our all medians equal, at least one median is different. Hopefully you all remember the difference between a median, a mode, and a average or a mean. That should have been week 1, DS 301. Everybody remember the difference there? Okay. So this is telling us that there definitely is not a statistically significant difference between our groups. So we now have 3 tests. 2 of them are this Kruskal-Wallis. The way it's set up now is always valid. Is it the best one to use all the time? Absolutely not. But is it always a valid way of analyzing data like this? Absolutely. The ANOVA that we had here, where we do not assume equal variances, that would also be as long as the data is normally distributed, this would be a valid result for everything that we do. And it says there is no statistically significant difference between groups. Using the standard ANOVA, where we assume, or we have that one extra assumption of equal variance, we find that magically there is a statistically significant difference between these groups. So which tests should we look at? What tests should we say are giving us the most valid results? Well, Kruskal-Wallis, again, is essentially correct, or a good method for everything that we do, says there's no difference. When we eliminate the assumption of equal variances, if they are equal variances and we assume that they're not, we shouldn't actually see a difference here, or we shouldn't see much of a difference, and we do. So what do we do? If we're going to report this stuff back to our boss, what medication should they be using? Medication A, medication C, or medication G? Based on our small sample sizes, and using the two most valid methods that we have, we can't see a difference between any of them. So what's the answer here? Tell your boss to go get more data. Another thing that you get to do, which is really annoying, is if you look at medication G and the data for it, you've got some values here that are negative. If we're talking about a medication, and let's say this is some sort of an effectiveness score, and we're looking at, like, honestly, yesterday I went to an urgent care facility where I was working yesterday because right now I'm going through an acute attack of gout in my middle finger, and it was hurting. They gave me a medication. Did it make me feel better? Yeah. But if I go to another urgent care that's closer to my house for the same issue, that medication makes me feel wonderful afterwards. So in this case, if we're looking at, say, pain reduction, both of them have um, positive reduction. So I hurt less after getting them. But maybe, say, you give someone one of these medications, and if they start to hurt more, what is that going to tell us? Or what direction is that data going to go? It's going to go negative, right? So sometimes we need to actually look at the data and make sure that the results that we have there are actually valid. If we're looking at these, let's say we realize that it's actually impossible to have a negative score here, but our data set has negative values. We can go back and we can try to look up those values ourselves and see why did they get put in as, say, negative. If it's something that's being pulled off a computer screen or pulled out of a medical record, has anyone ever done that before? Scrape data off of written text and then hope that everything works out well. And if you, what I noticed on the exams that all of you turned in, some of you had a format that looked exactly like the exam that I gave you. Some of you, when you printed it out, the format was completely different. So I'm guessing some of you opened it in Word, some of you opened it in Google Sheets, some of you opened it in, what is it, Apple Pages or whatever, then had to do a conversion. Some of you may have opened it as a PDF. And every time you convert these things, things change a little bit. So that might be an issue that pops up. Does it happen? Yeah. Does it suck when you have to go back and try and fix it afterwards? Oh, yeah. But if we do that, we realize that all the data that we've got here is valid and is the correct values in here. What's our recommendation going to be? Using the two most valid methods we have, we can't find a difference between these medications. So that can be an issue. Now, when we're doing these types of ANOVA things, I'm going to go back to stat, back to ANOVA. We're going to do a one-way ANOVA here. And instead of looking at just those three medications, let's look at all of them and see what happens. So you can highlight all of them. So I'm looking at A through G. Then I'm going to hit select. Under options, I'm going to leave this as assume equal variances. I'm going to keep that checked off, not on. Going to go ahead and click on OK. Everything should be set up and ready to go. Then I can click on OK. So now that we're looking at a whole lot more data, what is our p-value for this test? 0.003. Is that below 0.05? Yeah. Is that below 0.01? Yeah. So now, because we're looking at all the data we have, this is now telling us that there does seem to be a statistically significant difference between at least two of the groups we're looking at. Might be more, might be less. We can look at the standard deviations for everything here, and we can kind of see that we're thankful that we indeed decided not to assume equal variance, because I've got 21 or standard deviation of 21 here, the standard deviation of 2.7 down here. Are those going to be different? You betcha. The pairwise comparisons, again, trying to put everything into these different groups. What do we notice? It looks like medication H is in group B and not in group A. So basically, based upon the data we have here, we can say that medication H is different from, I guess, all these other medications, if we want to look at it that way. Or specifically, it's going to be different from medication C. We go to the next thing here. Dear God, does that look like a lot to anyone? So let's open this up in Word so we can see this a little bit better. So we can see that we are now looking at literally every single comparison. So AB, AC, AD, AE, AF, AG, AH, BC, BD, blah, 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 all the way down. And looking at all of these interval plots, we see that medication C seems to be different from medication H. And that is the only statistically significant difference that we see here. So when we're trying to interpret, oops, sorry. So when we're trying to interpret, what the heck does all of this mean? This is telling me that H probably going to be fairly different from C. We look at the interval plot. H seems to be statistically significantly different from C. Yay us, right? So now that we find that that's the only comparison here where there's a statistically significant difference. Looking at the individual plots, you can see it definitely looks like G is different. Looking at uh, the error bars for all of these, F looks huge compared to A through E. G looks huge compared to A through E. H looks a lot smaller compared to everything else. So again, if we assumed equal variances here, we would have gotten results. We'd have very different results, but our results would be wrong because we violated the assumption here that variances for all these groups would be the same. You can see the same thing here with the box plots. Again, looking at the QQ plot, do most of these data points seem to be on the line right there? Yeah, we have one outlier, whatever. We're looking at, I believe, what, 10, like 80 different data points. At 80 different data points, do I expect to see an outlier or two? Yeah. Where does that come from? Because you all remember everything you ever learned about the normal distribution back in 301, right? 95% of the data is going to be within plus or minus 2 standard deviations, which means 5% is going to be outside of that. If I have 80 data points, uh, I would expect that one, maybe two, would be an outlier. If I saw 5 or 6, I would say, okay, there's something different going on here. We need to investigate it further. But because there's only the one, and given how much data we have, I'm not going to worry about it. Again, when we look at the histogram here, we've got the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then there should be 12, 13, 14 different bars or bins here for the data. Again, we've got 80 data points. Take the square root of that, that tells us we should have probably like 9 bins, not 14. Is that going to change our opinion about whether or not this data looks uh, normally distributed or not? I would assume so. So I'm not going to worry about the histogram in this case anyway too much. But we have all this information. We can now go back and we can start talking with, say, our bosses or whoever about, are some of these medications different? Some things that can pop up on here as well. You might look at all the data and realize that maybe medication G and medication H or something like that, you don't want to analyze for them anymore. So then what do? You go back to stat, you go back to ANOVA. When you look at all the groups you want to test, you delete them. And then you go about your merry way of doing everything again. One of the more annoying things when it comes to doing these types of analyses is what? You don't do it once and go with that. You do it once, you check everything, make sure that your assumptions are holding true. If your assumptions are not holding true, or you're suspicious that your assumptions are not holding true, you go back, you do another analysis where you have what are called the relaxed assumptions. So going from we assume equal variance, then we relax that to do not assume equal variance. But with both of those, we're assuming what? Data is normally distributed or nearly normally distributed. What if that's not good enough? We relax the assumption of normality and do that non-parametric test that I was showing you. So again, it's not something that you do at once, you get the answer and it's done. And when we start doing a regression modeling starting next week, we're going to see, I can give you all the exact same data set. I can have you run the exact same algorithm in Minitab. Most of you will not confirm each other's results. For those of you that came to the talk that I gave in the math department, no, I have not put that extra credit stuff in yet. I will. And the whole talk was based on You have say 30 students in a class. Uh, we're all going to be writing answers up on the board. What we're going to find is because we're all going to be using something called a different random seed, everyone's going to have results that are slightly different. Some people may agree mostly with each other on what is statistically significant, what is important, and what is not. But there'll also be a lot of you that are picking up variables that are not statistically significant. So if you only did this analysis once, you'd only have your one opinion of a model. And because we can do it fairly easily, and you saw how quickly I could go through all these, right? It takes 5 minutes to get the right answer. Spend 5 minutes to get the right answer, right? So we'll be looking at that a little bit more. Just going back to the one-way ANOVA thing here, and also trying to get all of you a little more accustomed to some of the homework style of problems. Uh, I will post a homework problem, and there will actually be a homework on this ANOVA stuff. It'll be fill in the table and then do comparisons if needed. And when we're doing that, I'll write down here where it says a pooled standard deviation. That's going to be the standard deviation that you use when you start plugging this stuff in for t-tests, okay? And uh, also going to have you do, and I know you guys absolutely love this stuff, but what you're going to have is you're going to be able to create the confidence interval. You're going to have the mean, but this is going to be the mean difference between the two groups. And then plus and minus that margin of error. For everything we've done up to this point, the next step is what? We say margin of error is equal to a t-value times the standard error. Up until this point, I've been saying that this t-value is basically 2. What's going to be different about it this time? You're going to have the margin of error. From the t-test, you're going to have the standard error. That t-value there is not going to be 2. That t-value is going to change based on the number of comparisons you're making. Again, if we say the probability that all of our comparisons are correct is equal to the probability that we made each pair correct raised to the number of comparisons. So again, if I want this to be 0.95, and then this would be x to the, I don't know, let's say 12, x, so the probability that you do each of the pairs correctly is going to be 0.95 raised to the 1 over 12 power. Oops, sorry, 1 over 12 power. What is that value going to be? Come on. So if I'm just going to use my, and you can totally see what's on my screen right there, huh? Sorry. Uh, so 0.95 raised to the power of 1 divided by 12. And this is just as an example. I got 0.9556. So this t-value is going to be a function of that 0.996. So what's the thing that we're going to be doing here? Again, it's going to be probability uh, that someone confirms a conclusion. And you need to use the normal CDF. Our low value, it's going to be the margin of error. Our high value, for most of these, 1,000 should be good enough. Uh, the mean, so that's just going to be whatever X bar is. And then the standard error, it's going to be something that's already been calculated for you. Okay. So when we go and try to do this with one of these two sample tests with Minitab, so I've got the pooled standard deviation right here. Go to stat, basic stat, two sample t-test. And just going to be honest with everyone, uh, with the way that I'm doing it right here, this is something that you're going to do for the on the exam, but this is actually already done for you by the software that we've got. So summarize data. Oops, did the one sample. I want the two sample. Sorry. So summarize data. Sample size. We've got 10 in each one of our groups. The sample mean. Let's say I'm comparing a D versus G here. So 27.6 versus 12.57. For the standard deviation here, I'm going to use the pooled standard deviation. So 12.9 and 12.9. Our options, we're looking at differences here, and we're assuming equal variances because with ANOVA and with this type of ANOVA, that is the thing that we have to do here. Oops. And I also need to change the confidence interval here. So just again, based on what I just wrote down, our confidence interval is going to be 99.6. Then click on OK. You can see the confidence interval for the difference. Should give you, man, it's not even doing it. Oh well. Sorry. Anyway, it should give you the standard error for the test. And in this case, it's definitely not. You can go back here, try and figure out what that standard error is going to be. But again, you have to figure out what is the inverse t value for the 99.6% confidence interval. Since Minitab's not doing this for me, we're going to skip that part. We cool with that? All right. Sorry about that. So anyway, all the stuff that I just did there, don't worry about it. If you're using SPSS, it would give me all this stuff, and then you could do it really easily. So my apologies for that. Anyway, that's it for today. If any of you didn't pick up your exam last time, I still have a bunch of them up here.